Hi, this is Xingfen Shao from University of Southern California, and I have nothing to declare. So arterial spin labeling is a non-invasive technique to measure brain perfusion, and the label and control images can be subtracted to get a perfusion contrast. So ASL paper has recommended several parameters for labeling and recommend single PLD protocol for acquisition, but they suggest using a different PLD for different populations to avoid some CBF quantification errors in brain regions with prolonged arterial transit time. And multi-PLD protocol is also very popular because it can generate simultaneous quantification of arterial transit time and cerebral blood flow, but it takes slightly longer time. So the quantification accuracy and the measurement reliability has not been directly compared between the single delay and the multi-delay ASL acquisitions. So the goal of this study is to evaluate the performance of the single delay and the multi-PLD 3D grids pCASL via both simulation and in vivo test and retest data. For Monte Carlo simulations, we first generate a perfusion signal according to the single compartment ASL model and assuming some arterial transit time and CBF values for gray and wet matter. And we use a PLD of 2 seconds for single delay acquisition and a PLD from 0.5 to 2.5 seconds for multi-delay acquisition. We then adding some Gaussian random noise to the simulated signal to test for different levels of temporal SNR from 0.1 to 5. And we repeat step 2 for multiple times. So we choose 12 times for single delay acquisition for a typical 5 minutes ASL scan and calculate the CPF value, assuming the arterial transit time is shorter than the pulse-signal delay, as we assume the values here. And we can do a similar process for multi-delay acquisition. We repeat the step 2 for 2 or 3 times for each PLD, and we can calculate the CPF and the ATT simultaneously using either a weighted delay approach or a least square model fitting approach. And lastly, we repeat the step 3 for 5,000 times for Monte Carlo simulation. We can estimate the mean of the simulated CPF and arterial transit time to estimate the accuracy of the acquisition. And we also calculate the SNR to estimate the reliability of the acquisition. So all MR experiments were conducted on 3D Siemens Prisma scanner with test and retest interval about 8 days apart from 21 healthy subjects. And here's the parameters for our acquisition. And we use a relatively higher spatial resolution, about 2.5 by 2.5 by 3 millimeter. So here are the CBF maps estimated from one subject using the single delay and the multi-delay acquisition protocol. You can see it's very comparable between measurements. And here are the arterial transit time maps estimated from the 5PLD acquisition using the model fitting and the weighted delay methods. You can see the weighted delay method slightly underestimate arterial transit time in some brain regions. So here are the results of the Monte Carlo simulation. You can see the CPF values on left and the ATT values on the right. For the gray matter and the white matter. So the black arrows indicates the typical temporal SNR about 2 for gray matter and about 1.4 for wet matter. So the 5PLD acquisition, the CBF values are slightly overestimated, as you can see in the blue and the red lines here. And for the arterial transit time, the model fitting approach slightly overestimate, and the weighted delay approach slightly underestimate arterial transit time, but it's only about 1 to 5%. So for the single delay acquisition, the CBF values, the blue line you can see is very accurate because using our simulation parameters, the arterial transit time is always shorter than pulse-signal delay, so there's no error. But this single delay acquisition CBF values can be largely underestimated if the arterial transit time is about even 100 or 200 milliseconds longer than the pulse-signal delay we use. So here are the histogram of the arterial transit time distribution across 21 subjects from the model fitting and the weighted delay methods from 5PLD data. As you can see, majority of signal voxels has arterial transit time shorter than 2 seconds, but there are still about 7 to 15% voxels were estimated to have arterial transit time longer than 2 seconds. So in those voxels, the CBF values can be largely underestimated using a single PLD of 2 seconds. So here are the Monte Carlo simulation results of the SNR in CBF and arterial transit time in gray and white matter. So also the black arrows indicate standard TSNR. So the single delay acquisition to give you more reliable CBF quantification than the 5PLD approach, as indicates the black line here, especially the benefits larger in white matter. And for the 5PLD acquisition, the reliability of the arterial transit time and the CBF measurements is overall higher than using a model fitting approach, which gives about 20 to 40% of the SNR again. So here are the in vivo data. I'm going to show you the scatter plots of the test-retest measurements using the single delay CBF and 5 PLD CBF, 5 PLD ATT using the model fitting approach and using the weighted delay approach. So single delay acquisition, you can see the ICC is the highest among all those between the single and the multi-PLD acquisition. So indicates the best test retest reliability. However, the CBF values here you can see is about 10% lower than the 5PLD CBF values, which is due to the voxels has arterial transit time longer than 2 seconds. So for the 5PLD acquisition, the model fitting approach improves reliability of the ATT and the CBF quantification, indicated by higher SEC. You can see the model fitting results compared to the weighted delay approach. So in conclusion, we evaluated the performance of single delay and multi-PLD 3 degrees pCASL via simulation and in vivo test retest data. So the single delay on CBF gave you highest test retest reliability and shorter acquisition time. However, it underestimated CBF due to the prolonged ATT in about 10% voxels. For the 5PLD acquisition, we can get both ATT and CBF measurements with improved quantification accuracy in regions with prolonged arterial transit time. However, this slightly reduced the test retest reliability. So in terms of model fitting or weighted delay approach, we found the model fitting approach is overall better in terms of the quantification accuracy and reliability. So thanks for your attention.